Hello guys, welcome back to the channel. So the problem of the day for today is Leetcode 1863, sum of all subset XOR totals, which is actually this particular problem. But before we actually do this, this is completely a copy paste. This is completely based on Leetcode 78, which is subset. So today, before we actually do the problem of the day, we are going to talk about this particular problem, subsets. Okay, so let's have a look at what the problem statement says. It says given an integer array nums of unique elements, so every element is going to be unique, return all possible subsets, which is also known as the power set. So the power set is basically all possible subsets that you can extract from this particular uh, array. Okay, the solution set must not contain duplicate subsets. Return the solution in any order. You don't need to sort it or anything. Right, so let's have a look. If for example, this is my array, a very simple array 1, 2, 3. So the power set of it is going to be what? First of all, the empty array. Then I take all the elements singly. So 1, 2 and 3. Then I make pairs. So 1, 2, 1, 3 and 2, 3. Okay. And then I make 3, like combination of 3. So 1, 2, 3 is going to be the only combination. And then if it's 0, then obviously I'll have just an empty array. And so an empty array is also a subset of all the possible arrays, right? And the single number itself. For example, let's take this example. Okay. For example, I had 1, 2, 3 and 4. In that scenario, what would it have been? I would have had an empty array first of all, then 1, 2, 3 and 4, all of these, then pairs of 2. So 1, 2, you know, 1, 3, then 1, 4, similarly 2, 3 and 2, 4, right? And then 3, 4. Then I would have had pairs of 3. So 1, 2, 3, you know, then 1, 2, 4, then 1, 2, 3, 1, 2, 4, then 1, 3, 4, right? Then 2, 3, 4, and then I would have had pairs of 4. So 1, 2, 3, 4, something like this, right? So this whole set is going to be what? It's going to be the power set of this particular array. That makes sense. And what we have to do is we have to return a 2D vector. We have to return a 2D vector as the final answer. So the thing is, how do we go from our original array? How do we go from our original array to this particular answer? That's what we want to try to figure out. And there's this very standard, very easy approach for doing this. You see, let's take a smaller example. First of all, let's take an example of 1, 2, 3. Okay. And for 1, 2, 3, we already know that we are going to have 1, 2, 3, 4, 5, 6, 7 and 8 possible subsets. So 2 to the power 3. And it makes a lot of sense, right? You see, if you have just one element, inside of your array, so your the answer of that is going to consist of two things, empty and itself. Similarly, when you had 3 elements inside your array, the answer had how many things? 8 things. So 2 to the power 3, and this is 2 to the power 1. Similarly, if you had sorry, not 0, 1. If you had one element inside of your array. If you had 2 elements inside of your array, it would have been 4. If you had similarly 4 elements inside of your original array, the total possible combinations would have been 16. Let's actually count. 1, this is 1, this is 4, so becomes 5, this is 6, so becomes 11, this is becomes 15 and 16. You see, so these are all the possible combinations that you have when you have 4 elements inside of your array. I hope that makes sense. Now, what we want to try to figure out is how do we actually make, how do we, like, how do we explore all the possibilities? So there's this very standard approach which I want to tell you, and it's very, very intuitive if you think about it. You see what's happening. If you think about it, if you observe the problem statement and the thing which we are trying to solve, you see sometimes I take an element, sometimes I do not take an element, sometimes I take an element, sometimes I do not take an element. So 1 comma 3, I'm talking about this particular subset. Similarly, there could have been a scenario that I had taken these 3 and not this, so it would have been 1 2 3. Similarly, there could have been a scenario where I would have taken 1 3 and 4, right, and not taken 2, so it would have been 1 3 and 4. So what do I have? I am talking about choices. A simple, very standard choice, take and not take. You're getting it? We are talking about choices, and you see, whenever we are talking about choices, whenever you have an option, either to take the element or not to take the element, always think about recursion. This should click inside your mind. As soon as you realize, as soon as you know, acknowledge the fact, understand the fact that you have options, recursion is the way to go. So you see how you're going to do it. Right now I am at index 1. I'm at index 0. Do I take index 0 or not? I have two choices. Do I take it or do I not take it? So if I take it, my array becomes 1, right? Initially my array is, let's say, empty. If I do not take it, my array remains empty. Now, since I have made my decision for 1, now I will make my decision for the first index, which is 2. So if I take the 2, this is take, this is not take. Okay. If I take the 2, it's going to become 1 comma 2. Similarly, if I don't take the 2, this is going to remain 1. If I take the 2, is on this particular level we were talking about this number. On this particular level we are talking about this number. Okay, so if I take the 2, I will have 2 inside of my array, and if I don't take it, my array is still going to be empty. Now again I'm going to make the decision, and you can very easily guess at this level who am I going to make the decision for. I'm going to make the decision for this particular index. Okay, what's the number at this index? The number is 3. So if I take the 3, then I will append this to this subset, so it becomes 1 2 3. If I don't, then 1 2 remains 1 2. Similarly, you can very clearly observe this is going to, if I take the 3, then it's going to become 1 comma 3. If I don't, remains as is. Okay, if I take the 3, it's going to become 2 comma 3. If I don't take, 2 remains as it. If I take the 3, then inside of this I push 3. If I don't, I don't. So how many possibilities are these? 2, 2, 2, 2, 2 and 2. 8 possibilities. As simple as this. So this is the only thing which you're supposed to do. Nothing other than this. Now the question arises, how are we going to code this up? Isn't it? How are we going to code this up? Right. So what I'm essentially doing is, देखो, I'm taking an element, okay, I take an element and I explore further. Similarly, and this is something which I do on the left hand side. Okay, on the right hand side, what do? I do not take an element and I explore. Now, whenever I use the word explore, explore is just another word for recurse. Okay, recursively explore. That's what I mean by explore. So how are we going to actually code this scenario up? It's very simple. Let me actually show you. Okay, so over here, this is the function which Leetcode has provided to me, and they have given me the original array. Okay, what I'm going to make, ultimately I have to return a 2D array, right? So I make this 2D array. Okay, and then I make another temporary 1D array. Why do I make it? That should be your question. Why am I making another array name as current? You see, I'm keeping track of these arrays as well, right? At each and every point, or you can say at each and every state, I'm keeping track of these arrays as well. This array, this array, this array, this array. These are my different states, you can say. So in order to explore and in order to reach till these states, temporarily I would have to store them somewhere, right? Isn't it? So that's why I'm taking this current. Then I make a function which is known as solve, what it's going to do is it's going to take the answer array, it's going to take the current array, it's going to take the index I, it's going to take the original input array nums, and it's going to populate the answer. So ultimately at the end of the day, I have this inside of my answer array. And if you think about it, if you think about it, I reached point 3. Why did I not continue making decisions, right? Because as soon as you increment the I, you go out of bounds. So what would that be? That would be your base case. You are out of bounds. There is no more number which is left to explore. So as soon as you reach this particular state, you can say, by okay, all good, I don't have to explore any further. Why? Because I have explored the whole of nums. You getting my point? So the first thing which I'm going to do is I'm going to sort of make the function function definition, receive answer, current, I, and nums. Similarly, then what I'm going to do is, first thing, what do I do? This is my current, right? I push back the current number inside of it, nums of I. What is I right now? I is 0. You see? So initially, what did I say? Initially, my current is empty, right? My current is right now empty. I have passed it over here, and my index I is 0. What do? I push back nums of I inside it and then explore. So I make the recursive call. Okay, I further explore. What do? I say, okay, now go to I plus 1 index. So what will happen? I will go back over here and my index is going to increment. You getting my point? My index is going to increment. Then again, this is one call which I need to make. What's the other call which I need to make? Do not take index number 0 and explore. So that's exactly what I'm going to do. Pop back means remove. I remove this one and I explore. So take and explore, not take and explore. And I'm going to do this for each index. You see, I'm going to do this for each and every index. So if I made this tree in front of you. Now, if you dry run this particular recursive code by yourself, you're going to make the exact replica of what is present in front of you. Are you getting my point? So for each index, what you are doing, you are taking it and exploring further. You are not taking it, you are rejecting it and exploring further. And this is one of the, you can say, most basic template of how recursion works. Knapsack problem is also based on the same thing. House robber problem is also based on the same thing. And the problem of the day for today, sum of all subsets or totals, which we are going to cover in the next video, inshallah, it is literally a copy paste of what this question is. All right, now let's give the finishing touch. What is missing in this code? You are 100% correct. The base case, right? Because if I do this, it's going to run and run, and right now I don't have anything to stop my recursive calls, right? What do I need to do? I need to say that when my index is out of bound, so when my index actually reaches out of bound, I need to return. What do I need to return? You see, one thing which I'm going to do is I'm going to make sure that the recursive process stops and I return. Okay, something like this. I do not explore any further, I return from each and every state upwards. But then I have to do one more thing. What? I have to push all of these states into what? Into my 2D array. That's why I have actually passed it over here, right? And you can very clearly see I'm passing it by reference so that I can actually populate this. So that's going to be my recursive call. That's going to be my recursive call. If I reaches out of bound, what do? Whatever your current state is, you just push it back into the answer array and ultimately you return the answer array. As simple as that. So if you submit this particular code, let's see if it passes all the test cases, and it does. Okay. Now, one very important thing. What is the time complexity of this code and the space complexity of this code? If you think about it, dekho, what did I say? I explained it to you. When you had just one element inside of your array, How many operations did you need? You just needed 2 to the power 1 operations. If you had 4 elements, then you needed 2 to the power 4 operations, isn't it? Right now we had 3 elements over here. So how many operations did we do? We did 8. We had these 8 ultimate final states. So the time complexity is O2 to the power n, which is exponential. Okay, which is an exponential time complexity. If you think about the space complexity, then just think about what would be the space complexity of this particular code. So you see, we are taking a temporary current array in order to maintain all these states, and ultimately we are taking a 2D array. But then that 2D array doesn't count as extra space, because we obviously need to return it as part of the answer, right? We need to return a 2D array. So that I think won't count as extra space. But then we are taking, you can say, O of n extra space over here. Why? Because at max you are only going to store the whole array inside of the whole original array inside of a particular state, like in this scenario, right? But then there's the recursive tree stack space as well. So count that recursive tree stack space as well. So we need to consider that as well. So that's it from the problem of subsets. In the next video, what we are going to do is we are going to copy the same code, the same strategy, and solve the problem of the day for today. So I hope the video was useful, and I'll see you in the next one.